Okay, welcome back. So let's just continue with what we plan to talk about. And I said I start with the third evidence, and now just really talk about implementation because this is empirical. And I'm going to show you how we actually do this without the full technical detail about implementation because I'm going to have a separate section to talk about implementation itself. But roughly speaking, now the question here is that we have the QHD algorithm, right? And we try to see whether there's a way we can implement that on real machines so we can do some empirical study. And of course, you come out some instance, you run this also with classical solvers, that'll give you the classical performance. So everything now become real machine implementation and also empirical. Again, so theoretic machine. So this is the Hamiltonian want to simulate, and just in theory, this is something can be efficiently done. Actually, my colleague Andrew Childs has a paper talking about how you can simulate this like a Schrodinger operator in real space. But if you do a little bit of resource analysis, which I don't list number here, but I did have in the paper we have, you're gonna need at least 10 billion gates for getting this running. So that's pretty pessimistic, right? So you cannot run this anytime soon. And actually that's the situation we had in 2022, right? So we have this algorithm. We really want to see how empirically performs. So we do the simulation for 2D. That's roughly can push the simulator out to solve maybe 5D, but that's the limit. Can you go all the way to say 100 dimension? I think they're potentially going to see something, but we don't know how to do that with the classical simulation. We need to think a way out. And that's basically the question we have. Digital basically too expensive to really run this. And by the way, I should say, how we can really circumvent this is really coming from the very, very basic intuition. We get to the point. We say try to find the algorithm without circuit description, right? So this algorithm is a algorithm without circuit description. This algorithm is a Hamiltonian simulation part, by itself. And this is also the potential reason we can get rid of this digital circuit resource bound and try to do something more creative. Again, I should point out that there's another thing which in theory word this I think totally legal, but probably not that legitimate for in practice. That you can imagine maybe you can build a machine just run this Hamiltonian, right? Then you can run this very nicely. I can tell you this might be something in the some distant time. If you really want to implement this term, you really think about building like a bosonic modes in your system. And there are people thinking about how to build that machine for simulation tasks. So this is really bosonic modes. And you want to make this function non-trivial, you need three-body interaction from bosonic modes. So probably not that too unimaginable, but that's not the way we're checking here. Still, that machine does not exist. But I think people are trying to do that for some many-body simulation tasks, especially maybe Fermi-Haber mode, mode or something like that. But anyway, so we didn't go that route, and we don't have a machine that implements this particular Hamiltonian. Now, how can we get around it, right? So just coming back to this picture, we say what I show you is the digital simulation. We have something provably to work, but it costs like 1 billion gates. Now, we try to seek alternative. The alternative here is thinking about maybe there's certain kind of a machine with this Hamiltonian directly running this Hamiltonian. That's a wonderful case I just mentioned. If I have a bosonic system with three-body interaction, that's good. But we don't have the machine either, right? So then you need to be more creative. Can we have some machine that is ready today, even though non-perfect? But that particular Hamiltonian can somehow be used to simulate this Hamiltonian. And that's the entire technique we're developing here. We call it Hamiltonian embedding. And I have a separate section just talking about how we do that, the theory, construction. And of course, there should be no free lunch. So that means you cannot just imagine, using this, you can save the resource for everything. That's not the case. But there are definitely cases where using this approach can bring you together, closer to what the machine can do. So this is essentially a trade-off. I'm going to show you more, later in the section. But for now, just assume this is something going to work, and it's especially going to work for this QHD Hamiltonian. And in particular, with that technique, we basically say you can somehow embed the Hamiltonian you need for running this particular quadratic programming instance, which is box constraint. So everything is high dimension living like a unit box, and you try to run this particular quadratic programming. So this probably is a general NP hard if you have like indefinite queue. But of course, that really depends on what a queue looks like. So there's another caveat for running these experiments. This is essential because we're embed this Hamiltonian into this Hamiltonian. This is a quantum IC machine. And we don't have any other candidate than D-Wave at the time. It's still today, I think. That has a lot of qubits, even though they're not the perfect, or actually maybe far from perfect. But this is a Hamiltonian you have. It's a huge IC machine, right? So you have like a local interaction, some neighboring interaction, neighboring ZZ, local Z, local X. So we have a way to embed this Hamiltonian we need for QHD into this kind of Hamiltonian and running those on D-Wave with two caveats. The caveat one is that I cannot choose any queue that I want. And you can imagine if I make this queue more complex, the problem will become harder. But the more complex queue here means that I potentially need like a better connectivity to really get like an interaction between different like spins. That's limited on D-Wave, so I cannot really generate very dense queue. Okay, that's one caveat. We can only generate the queue that can be somehow mapped to the D-Wave connectivity, which is already not too small. I think the sparsity rate here like is 6, 7, so it's not very small. And we basically randomly generate those instances here. So another caveat is that if you ever work with D-Wave, they used to have like a free account for academia. They don't have that anymore, unfortunately. You cannot really easily program this schedule. So because it's really designed for annealing, so they have their built-in schedule. So you need to somehow engineer their system without using their high-level software tool. You need to go back to their backends, sending instructions, and basically using your mapped Hamiltonian, using a mapped schedule. So that's the true thing we change their machine to do for our purpose. But this is, again, some kind of approximation of the Hamiltonian. So let's see what, so this is what we have at the time of maybe 2022. And then this is something we have today. Today means that we basically do everything for you in one software package. So usually because you need to do everything when we look into our code base, but now we have a software for doing that, automate everything. So you just need to type in your optimization instance, and the software can try to do all this mapping for you, and then of course send to D-Wave, but it's no longer free to academia. It's expensive to run that for now. So I don't know. IonQ, we did the experiments at the time, only can run for a very small instance. For that small instance, it's good, but it have very limited number of qubits. And with that software, especially in the past year, there are 3 more like an application domain paper making use of this kind of software to try to use that for some like real application with quantum. Of course, this is at a small scale, as you can imagine. But this is hopefully some way helping people to really leverage this tool without even understanding all the details. You have a question?
Yeah, just in terms of D-Wave's connectivity, was it literally just nearest neighbor?
No, it has a more complicated graph.
I see.
So it have I forget exact name. So they have they really need a high connectivity because for optimization problem. So they try to hardware engineer some graph where they can use the graph native connectivity. I think maybe around 8 or maybe 10 or ish. Definitely more than neighbor, nearest neighbor, and then with also some kind of minor embedding they have, they can somehow build in much, more, much richer connectivity. Yeah, but whether that's faithfully doing the annealing, that's a separate question. But just mathematically, that's one.
I see. And then in terms of this caveat that you gave, what what kind of further improvements on
So,
connectivity would you
okay. So basically, what we do is that we have mass tell you how you embed this Hamiltonian into this shape, but this shape is not what the hardware of D-Wave can give you directly. And so we didn't do any innovation here. We say, okay, we give this shape, a desired shape of Hamiltonian into D-Wave's own compiler. So D-Wave will say how they can map this particular shape of Hamiltonian into their own IC machine connectivity. So we didn't do anything here. So we just say this is a particular shape the IC Hamiltonian we want. Yeah. So that part can change. If you have better solution, maybe you can change the performance. But we didn't do anything there. Okay. Of course, now we have the software. Now let's just try to see what we can use the software run. Hopefully, probably you cannot run yourself today. You need to buy theirs. But the latest one we run is like last. I can show you what we have. So I basically show you two kind of results for this empirical study. One is for dimension 5, basically like a sanity check case where I can simulate everything. I can simulate everything. That means I know the perfect QHD behavior. And also I run this against many classical solvers. So those are the classical solver we're testing. And for that particular quadratic programming Bach constraint problem. And we use the time to solution as the measure. So this is basically our very standard measure in this domain. You calculate how much workout time you need until you reach maybe certain success probability for getting the correct answer. And because for our scheme we have both quantum annealing time, also a little bit of post-classical processing time, so we count them both. So we add them up. So then this is the picture. So this is a log. It's a log of the time to solution, and this is a compare against different solvers. So the same QHD basically says this is the running time if you have a QHD running perfectly. So basically this is a classically simulated QHD's performance. So everything will be perfect. Then you can see this is way better than anything else in the class against the classical other solvers. But when you try to run QHD through D-Wave using the way I just showed you, it drops to here. And this basically says, okay, we know D-Wave has decoherence, and this is basically how you see this kind of decoherence on this machine. And that affects your effect for solving this kind of problem. Okay, so this is it's noisy, but it's expected. But what we should see is that even though running this on the noisy D-Wave machine, it still gives you better physical work clock time than other solvers. And this is also including if you run this with QAA, but running this on D-Wave. D-Wave has like a native QAA, quantum adiabatic algorithm to run that. So that's what you can see for dimension 5. Okay. Yes.
Maybe a naive question: Is it obvious that decoherence in your quantum machine only makes you slower, but you can still find the right solution?
It's not something I can explain. Yeah, I don't know. The honest question is that it can go either way, but just empirically you see it makes things worse. Yeah. Because it really depends on your instance, depending on your machine's specific dynamics. The combination can go either way, but in most observation we see it just makes things worse. Yeah. Okay, so now because we can do this and we try to push this to the extreme. So the maximum thing we can really embed into the machine, I should say this is with their software tool with 2 years ago. And I don't know whether they improve the tool, they improve the hardware, they can do better. But 2 years ago, I think this is good enough. We embedded problem all the way up to 75 dimension. So this is really a large dimension problem. Again, we try to compare with other solvers, and then we don't have a ground truth. I cannot simulate the QHD up to 75 dimension. But what do we see? We see the D-Wave implement quantum QHD is still better than everyone else. This including a D-Wave based quantum adiabatic, and actually quantum adiabatic is not the best. SNOP actually is really designed for high performance, it can run faster for those problems. So in terms of the metric we're seeing here is that D-Wave implemented QHD is still better than many classical solvers. And if you believe this is a lower bound for performance for the actual QHD, so that was be evidence suggesting QHD would be even better, just empirical speaking. Okay, but I should point out, so the problem is not very hard. So you see, we're really talking about solving the problem in seconds or smaller seconds. So you're not really trying to solve a super hard problem. That's for one thing. For another thing is that if you bring grouping into the picture, which is not anything like this over here, so this is really like a branch-bound algorithm. So really try all possible combinations. It's a very clever, like exhaustive search. QHD actually is not good as, cannot be groupy in those cases. And of course, like nobody can really beat a groupy today. So this is really, highly engineered like a solver with a lot of heuristic. But if you could believe this is the problem will becomes like harder if we can go large dimension, maybe with high density. But we don't know whether QHD can really beat that in this case. But I did show you an example where QHD can beat a groupie early on. Remember, I have this high dimension asymmetrical double well. So yeah, so that means like if you can implement that, you can really beat the groupie. But for loads problem, probably not. And we know there are limitations for D-waves connectivity and the machine's decoherence for the performance. But still, I think this give you try to give you a sense for two things. One is that there's a way we can use D-wave to implement QHD, even though I haven't told you how to do that, right? So the second is that from the empirical studies suggest for like just like a random instance coming from this class, it runs reasonably good. It actually beats many classical solvers. Okay, and if you are interested to see how, yes.
And this is you asked first. This is over one instance of the Q?
No, this is a lot. This is
okay.
Like
so it's like disorder average.
Yeah, so this average. So this is like the range. And this is the median. This shows some like the core. This is the quarter here and this quarter here, and this is randomly over like a 50 generated instance.
Oh, okay, sorry.
Yeah, it's not one instance. Yeah, we try to get rid of this statistical.
You said you don't have ground truth, but I imagine that whatever the solver spits out, at least you can check that it's a sensible.
Yeah, I don't have a ground truth for the actual QHD runtime.
Oh.
Yeah.
But at least the
I have the ground truth for the optimal solution.
Yes.
I don't have the ground truth for if I run QHD, what it will.
No, I understand.
Yeah.
But so I assume that all these runs produce a meaningful result, at least.
Yeah. Because optimization is a really interesting problem where checking the quality is very easy. This is different from simulation, where you don't know the ground truth and you don't have a way to verify that. So this is actually a very sweet point. I think you have a solution, you know the quality of the solution. Yeah. Okay, so now because we have the software, so running this becomes super easy for us. This is like historically, so we put all this D-wave, QHD, QA with a different D-wave version. Used to be free, but then this 7.1, we need to really ask for access to get that. But anyway, so historically, you see, D-wave machines improving just a little bit over the time. So at least not going, just get worse. So the machine is improving. I think this can be some benchmark to show that, but not by a lot. But if you use our software, you can easily observe this.
Did you also try ChatGPT?
Yeah, the network latency will kill you. Okay, so now, so this is something. If you haven't heard the QHD talk I gave, in the past, you probably know everything I talked. But this is something new. This is something basically my former student and I spent quite some time working on in the past year. We're basically puzzled by the fact that there's a QHD we can empirically run, but we can only run on a small scale, and we cannot hope we can have a good quantum machine anytime soon. But there are tons of real world problems that you need to have empirical study to know whether your algorithm work or not. We cannot really prove, say, your algorithm work for this domain. This is really unrealistic. So most cases, you have your solver and you try to work on the real instance problem. Empirically, you can see things work or not. So we need some handle here. So we need to find a way to really probe the applicability of the quantum algorithm in real world. So, so this is our proposal for how we can really meet that in between. So we say, how about we come out with some classical algorithm, I should say, but we call quantum inspired, but quantum inspired means a lot of sense. So this is what I mean by here's that. So we try to find the classical dynamics that has certain feature of QHD, but of course it's not every feature because it's classical. So beyond that, it shares the exact same interface. So the way you model problem is the same. The way you solve, you output your solution, or you turn your classical whatever domain problem into the formal optimization problem will be exactly the same when you can run QHD. Except I just changed the underlying dynamics from the fully quantum QHD into something we call the quantum-inspired Hamiltonian descent. With that, we hope is that once you use this as a probe to test the the real-world problem, you just have one line change of code. You can plug in QHD if you really have the quantum machine to do that. I don't know when that happened, but it turns out this thinking really helpful. So I won't really get to the details how we design this QHD. I think we have a paper coming out soon. But this is give you some intuitive understanding how this is different from the QHD. So this is a QHD performance. If you have this kind of landscape, you see the huge tunneling happening to here, and everything is really peaked. But this is what the QHD will gonna look like for the same function, which is the red curve. So you see something happening, but not like this. Sorry, this is the QHD. This is the QHD. So you see something still left behind. So this is what the quantum is going to have. This is what the QHD is going to have. But anyway, so there is such thing, and to fulfill our goal to do more like empirical study, we actually have a version make this work on GPU. So it turns out this is a super nice thing to work on GPU because it's just like some physical procedure, right? So you just simulate that physical procedure, can run on GPU. We have actually open source version. You can actually find this version. We have one version put online at least. So there's something, if you're interested in running, you can actually try. And if you just have like a consumer grade GPU, you can run up to 100,000 variables. So that's a huge number of variables. And with that, we can do a lot of things. So let me show you something we tried. That shows something working, of course. There are more things we tried that are probably not very promising. So we basically find two types of problem where this particular solver is useful. And of course, it's showing something promising. We still need to get to since end to end. So one is really in like a medical image in this domain. We're basically solving problem, try to generate like a radiotherapy treatment. And this is a domain where you have tons of like image data, and those image data, it's coming from like your CT scan or like MR. So it's really about human. There's no human structure, and this is a problem. It's dense, it's large. There's no human structures, and turns out we can solve problem. Especially this is like a therapy generation problem in that domain much faster than the commercial solver people use it today in a proton therapy machine. Of course, this is really picking up part of their computing procedure and try to analyze that. So this is not end-to-end for now, but just that particular step, we can see a very large acceleration. And for that one, we really need to use at least like maybe close to like say 100K variables in solving this problem. So there's another domain we found this QHD is also very promising. That's for really compressing the models for foundation models. In fact, when I gave this talk maybe like 3 months ago, I say this will be something we can deal with millions of parameters. So that's like small model. You can find open source model like their GPT models, or maybe their small one from like Llama. And recently we tried do better engineering and try to solve for larger model. We can all the way to get into 7 billions model. So this is really something working. People can use that to do a lot of things. So we can somehow use this solver to do compression. And we see this improves the state of our compression rate than the classical methods. Of course, as I said, like these are preliminary findings. We hope to really see how much this can go. And all these algorithms are coming from like the ideas we discovered from QHD. Of course, quantum could be better, but thinking about scale here, this is not something quantum can deliver anytime soon. But with this idea, you can see this benefits in implementing GPU, and empirically you can see this. If you're interested, of course, I want to say, if you try to solve this with Groovy, then it's hopeless. It's too large for Groovy to do anything. If you're interested in this direction, we do have an open source version of this and that is available, and we have a paper on this coming up. Okay, so now let's just move on to what in the detail for how we implement.
But Xiaodi, isn't this in a way bad news, what you just said? It's great for medicine, I'm sure, but isn't it a case of taking the tricks from quantum and importing it over to classical, and now quantum doesn't have an advantage anymore, really?
You can put it that way. No, I think the thing is that for me, I gradually just taking. This is more like I try to solve a problem. Either I can do quantum or I can do classical, or maybe I come from quantum first and I find a better classical. Whatever it works, then I win.
Sure.
Not necessarily quantum will win, right? So, but I think that's a general thing for saying for particular application whether quantum is going to win or not. That's actually there's a high risk there because you're always competing with better classical, better quantum. But I find this is something empirical study totally open the venue for do more empirical study. Because before that, I don't know. I mean, I stopped. I just with theorem proof, with small case empirical, I just stuck there. I cannot do anything. But with this, I can imagine more. And actually, because of this, I realized, say, for the quantum solvers, what are the potentially real application values? Because if you look into the domain, one thing you learn more is that it's not the actual time to get to the optimal solution is only metric. It's also not the solution quality itself is the only metric. It really depends on your application. Sometimes you need say for example, sometimes even Groovy take more time, but Groovy can give you proof, say, how good is your solution. But all the quantum algorithms today, they cannot tell you how good your solution is. So for example, for people we say in finance, they really want to say I get the optimal strategy. I can take more time. I mean, also I can say I can buy a really expensive hardware, so that's not an issue because I'm doing finance. Any gain is a huge gain. So they really care I'm getting the top solution. But quantum there is really hard because quantum can generate a solution. There's no way I can prove the quality of the solution. And also, in most cases, I should say, heuristic algorithm really is the best one to run for practical solutions. And it's not clear how we add those heuristic into quantum algorithms. And so that makes things really hard in the sense that you try to use one simple quantum algorithm, you try to beat, in certain domain with this highly optimized, highly, heuristic, with a very good, heuristic classical algorithm. And you try to just say magically that's going to happen. Unfortunately, I think that probably won't happen. But this is only something you see when you are able to do this heuristic study. You're going to see more where what quantum algorithm today, what's the feature of the solver can provide you can really lead to some real application where this kind of feature will be enough. You don't need anything more. So I should say the two applications I identified has this kind of feature. I don't need the guarantee of the global optimal. I really want to solve this fast. I can tolerate a good enough solution. And that's actually something quantum can do, right? So that means if we can identify application domain where that's true, and quantum can do very well. I mean, of course, you need a quantum hardware to do. Then you're closer to see which is the right application domain. where quantum can be really useful, has commercial value, I should say. Okay. So in that way, I think I interpret this still as a progress for understanding the real quantum value. But maybe for as a bipolar attack, if I can really solve this with the GPU today, I'm still happy, right? So.
Okay.
Yeah.
I didn't quite fully understand the QIHD, but like, given that you could do 100,000 parameters, like, would making quantum hardware better to do QHD for the same problem even?
Yeah.
Provide any value?
Yeah, that's true.
Why would I do the quantum hardware?
I guess this is the question about like how scalable quantum could be in one day, right? So there definitely had a problem where QHD cannot solve, but maybe QHD can solve. So maybe just for this particular problem, if your GPU is good enough, there's no need for quantum. This might be the case even for some simulation tasks where your maybe tensor network method is good enough. This is for quantum. ML method is good enough. There's no need for that could happen. This is just say this also appears in optimization domain. That's the same. But only when we know where your classical competitors can win, and there's no clear win for quantum, better about like where you should look for quantum can have a real win, not a hypothetical win. You want a real win, then that's a pinpoint for people. There's no other alternative. Quantum will be the only solution. You'll be more confident about that. So in this sense, that directly give you the answer, but tell you where you don't want to go. Sorry, this is not directly relevant to the technical content. Yeah. But anyway, so let's just move on to talk about how we do this, right? So what's the idea for emulating your target Hamiltonian in a machine Hamiltonian where they don't look exactly the same? So first of all, just to recall it a bit, when people talk about quantum simulation algorithm, they usually talk about or they usually make use of some conventional input model. I should say, convention means they're most appear in most reference. Actually, the top two will be the more like a dominant one. So the very standard one, say just assume you have some oracle where the oracle encode the information for your Hamiltonian. And basically, you can say I can in superposition query say the maybe S and in S row JS column the non-zero entry, and they're going to return that. And of course, all this quantum algorithm are going to say, given this kind of oracle access, what you can do after that. But if you really want to simulate some Hamiltonian, you need to build this yourself, right? You need to build this oracle in your implementation. And this turns out to become the most difficult part, non-trivial part. If someone ever programmed a quantum simulation algorithm, you're going to see this is the most time-consuming part and very easy to get wrong. And of course, we know with the cubitization, so you can also take in a model called like a block encoding, where you basically just assume there's certain unitary, which is the some like upper top diagonal is exactly the thing you want to do, but of course you embed that into something large, and you assume that can be implemented. That's also assumed oracle. Again, in order to do that, you need to build the encoding yourself. So those two are very popular in theory because it really makes things easier to analyze it theoretically, and people usually use a query complexity here because this is really oracle, so you just count queries. But of course, for real implementation, this is the overhead. So this is the overhead that you need to think about, and I think, in fact, this will be the major overhead. In most cases, at least for today, this will be, accounts for the largest fraction of your final circuits. You can also say, how about I try to be a little bit, a white box. So this is another model people use. They call it the polyaxis model. So basically say, I try to describe my Hamiltonian in terms of the poly basis. But then because the poly basis are, for large Hamiltonian, I need to run through all the bases. So that's going to be exponential. Of course, sometimes, for Hamiltonian, you can have succinct description for that. You don't need to go to the exponential, but this is really something really hard in the worst case as well. So, but anyway, so those are the things that people usually use, mostly using those two for theoretical result. And this is something people use to try to get experiments because this is something close to the experiments. So what we try to do is directly say, can I just assume my machine can do this? So this is really, actually, I even do something even simpler than this, but right now this is the rough idea. Can I just say my machine can do some Hamiltonian, which consists of like one local term and a two-body interaction? If I think this is about the Ising machine, then this will be just the single XZ and a ZZ interaction. So this is exactly I just mentioned in what D-Wave can do. Now the question is that can I say, I have this something my machine can do this. Now I try to do something, the target Hamiltonian, what the target Hamiltonian looks like. So then this is refer to the Hamiltonian embedding technique, and which we have a separate paper just talking about that systematically. So the rough idea is that so one thing is that if you have any Hamiltonian, you can always use in the oracle approach. You can use you can build oracle in principle. You can implement a circuit. You can get this down theoretically speaking. There's no principal barrier for doing that. It's just that it might be very expensive. Very expensive in the sense that you try to generate a circuit that is very deep. In most cases, you can try to use like a smaller number of qubits, try to leverage the entire Hilbert space of that. That means you need to generate a very deep circuits, and that's something we cannot do because generate deep circuits require very good error rate for gates. So at a very high level, what we're trying to do is to say, how about we try to embed this particular Hamiltonian evolution, which requires really deep circuits, into some much larger system. But instead of running very deep circuits or deep evolution, I try to run very shallow circuits. So this is really some kind of time-space trade-off. And because of that, there's no free lunch. I'm going to comment on that. So roughly speaking, in the case of QHD, so I want to emulate the QHD Hamiltonian. So of course, I assume you need to do a little bit of pre-processing for that. For example, original QHD is in continuous domain. You need to do some spatial discretization, your term PD into ODE. So that's something you still need to do. But then after that, you don't really get an Ising machine, right? So it's still something very different from Ising Hamiltonian. So your machine had this Ising Hamiltonian. So this is different from this. So they're different Hamiltonian. Now, the Hamiltonian embedding idea basically say, I want to find a subspace of this large Hamiltonian, such that my machine's native Hamiltonian, when restrict to this Hamiltonian, when restrict to the subspace, it will be looking like the QHD Hamiltonian, or maybe add some time Hamiltonian you want. When you try to do this, you say, okay, nice. I just need to prepare my initial state in the subspace and evolve this Hamiltonian. Then when I look at this particular subspace, it will be just evolving the QHD on my initial state, right? So that's the nice thing. But that's the same when you ignore their off block terms. The off block term basically say it might be possible even you start with some state in this subspace. When you evolve the large Hamiltonian, you're going to leak to its orthogonal space. So you're going to see some a leakage error. So basically, if you can ever find a construction like this, right? So you start with the desired Hamiltonian, you run your physical Hamiltonian, find a combination of the subspace. Then you're basically facing two types of error. One is that when you restrict this Hamiltonian to the subspace, how much different this is from your target Hamiltonian. The other is that what kind of leakage you're going to have to run, when you run from this subspace, and you're going to leak to its orthogonal subspace. Unfortunately, we don't have any construction that everything's perfect. It means that we always need to have the error here and error here. So every construction we have for Hamiltonian embedding is approximate, but it's really up to how much you can really control those errors. So how we can make this more rigorous, mathematically speaking? So this is basically say if you can ever find embedding for some kind of Hamiltonian inside a larger one. So A is your target, H is the the physical one. So you say somehow and the physical H should be very close to a block diagonal one, up to a small rotation of my space. And the small rotation really referring to the leakage error. And at the same time, when I rotate my Hamiltonian to the block diagonal ones and try to find its distance to my target Hamiltonian, that one also bounded by some small error. And when you have those two conditions, you can basically say, if I just use the large Hamiltonian and look at the subspace, project to this, look at its support on the subspace, and try to see how much is different for running my target Hamiltonian, it's going to be bounded by those two type of error, linear in T. So this is going to be the general theorem. Of course, I haven't told you the construction, but this is the general theorem. And so one thing, if you're somehow familiar with the Schur-Wolff transformation, which is exactly how people use in this domain for like some perturbation, perturbative constructions, this is exactly the same mass. So this is the condition you're going to see from the Schur-Wolff transformation. We're also going to use here. Okay, so and the general way for us to really identify construction. So I talk about the general condition, and when you satisfy general condition, you have this like a Hamiltonian embedding like a error bound. But how we can construct this something like this? Of course, I should say there could be multiple ways. The way we come up with, especially for the instance we found, is using a perturbative construction. So the idea is that you try to find some Q, where Q will give you the desired construction of the structure of the matrix. The Q, of course, you still hope that to be something you can implement on your hardware. I'm going to show you examples and what makes this more concrete. But at the same time, you're going to, because you want to really have like a large provision for the leakage to the hive space, so you need to really treat a Q as some like a perturbative term to a huge penalty term that really push you down to the ground space. And you have the G here to really create this energy gap to prevent you from leakage from the subspace you start with to some orthogonal ones. And of course, at the end of the day, you basically try to simulate this particular Hamiltonian. And that's the general way we do the construction. Of course, how you come with this and this, right? So that's the question. So let me show you an example. So this is just a very simple example. Assume your target is to really create a subspace, which with like the 1, 2, 3, 4 as your vectors. But you want to create this kind of connectivity. You want to create like one-dimensional chain connectivity. Why do I want to build this? So this will appear very naturally if you try to solve, let's say, a PD problem, or I say ODE problem, for example. You're going to say this is really, you put the grid along the line, you're going to have a neighboring interaction. So this is going to be a chain. But this chain is not something you can easily have, say, if you have this actual Q being poly operator in tensor product sense. In particular, if we imagine what the Q, if something like this is like a single sum of the poly X, this will create a connectivity like this. So why is that? So Q will summation of your local X. So this basically means for whatever like the Boolean string start with, it will be connected to any other Boolean string that differ with the current one by Hamiltonian 1, because I'm going to flip one of the the bits. So that will create this kind of cube structure. Right? So that means a local Hamiltonian will give you only this, but you want something like this. Now, how can you making sure you can run with this kind of connectivity, but only with this kind of interaction? Now, this is the place I need to add a penalty. So the penalty here really say, yes, I know you have this kind of connectivity, but I want this. So of course, this is really something called a unary encoding. I want to pick those 4 vectors. I don't need every one of them. Those 4 vectors, when I project into them, will give you the desired connectivity, which is a chain. Okay. But if I directly apply Q on this chain, I have trouble because I can connect to something outside this subspace. So this is referred to leakage. Now the question is that, can I have the penalty also with just like a local, 1 or 2 local Pauli operator, somehow that can push my desired subspace to really low energy, but everything else with really high energy. And this construction here shows it works. And for this particular choice of the penalty Hamiltonian, for everything here that I want, it has -2 energy, and everything else has +2 energy. So you create a gap which is 4. And that's basically how you put into the construction here. So you already know gap is 4 and times g. So the entire gap is 4g. So then that really helps you to suppress everything inside this chain. And then if you look at this chain, you really evolve like solving an ODE dynamics, not really like in doing a quantum local Hamiltonian dynamics. Is this clear in the high level? Okay, good. And of course, we have more examples than this following this kind of idea. And actually, we can do for a chain, we can do for a cycle, and we even know how you can do this for any like maybe band or maybe aperture shape. And you can do this for, yes.
You do this by hand, or you does it, your auto does it automatically?
You repeat the
Smaller
question.
number of qubits, a smaller number of sites, it's easy to do so, right? Like the way you instruct.
Yeah. So
you have more, it feels like more difficult.
So we have an analytical form for the construction. But we didn't have a software code to do that. We can make that if you think this is useful. This is not hard. But we have constructions, and there might be even better construction than what we have. So we show this is possible. You can search for a construction actually if you have more hardware limitation. But anyway, so I think this shows that this kind of thing can work, and you can find maybe more constructions. So this can be something for 1 dimension, depending on what kind of like a topology you need. And you have a way to really build from this 1 dimension to high dimension. So we have a few composition rules to tell you how to grow from 1 dimension problem, maybe find 1 dimension ODE up to say n dimension ODE. Okay. So there are rules for showing how this kind of Hamiltonian building compose, and there are specific encodings you can use for showing construction for 1 dimension. Now, there's some technical remarks that I try to make here because I only give you since a high level. Even though I won't dive into the high level, the details for that, but still I want to give you another high level message, so making sure you have the complete picture. So what we're doing here is that we really try to do white box Hamiltonian simulation. So there's no oracles. You tell me explicitly what your Hamiltonian looks like. I try to find the Hamiltonian just to implement that. Again, so this is a time-space trade-off. So that you don't imagine there's like free lunch. You can solve this in the worst case, still have like a huge asymptotic save. It's not like that. And one motivation for us especially is we try to do this for sparse Hamiltonian that appear more in scientific computing domain. That's where you see this chain structure really useful. So I should say this is really a way to try to getting a sparse Hamiltonian into some like a local Hamiltonian. So this is what the tool is designed for. So you should separate this from other work like reducing the locality of Hamiltonian. So there's such an work, right? So you have like 3 local, I try to turn to 2 local. They're also to other, so that also means this can be combined. So maybe you can use this to get 3 local, then you try to have a way, maybe use the perturbative gadgets, you go from 3 local to 2 local. So you can do a lot of things here. I mean, I don't know what's the best design, but it just show this is possible. And then another thing I want to say is that even though you see this is no free lunch and some construction does not seem very clever, we show in a few cases, even with this kind of implementation, you can still have theoretical speed up remained. So what you really pay here is more like maybe you have like a error dependence which is like a log 1 epsilon. When you use this kind of implementation, that will become like a 1 epsilon, something like that. But you still have like a good dependence on the dimension. In fact, we have we use this technique for QHD, and we have a upcoming paper about PD solvers. So we're going to post it online. Okay. So, and how this relate to some existing physics literature? I should say, if I give you the specific constructions and maybe you're working, maybe in experimental physics, at least I know, you're going to see this construction are not so unfamiliar. So there are a lot of in similarity because we're going to use like a unary embedding or one hot or like we also use like antiferrometric things like that. But we built like a unified framework for doing this for sparse Hamiltonian, which is not something physics has a lot of interest in, but this is for scientific computing. We have a lot of interest in that. And another thing I want to point out, this is the very, I learned that this is something people also use a lot in, AMO physics or maybe other physics, experiment physics, using the Scherf-Wolf transformation, but they're not using this in our way. I want to just put it here so you know the picture. So in our case, we say we want to emulate your Hamiltonian here, right? And the leakage error is something we don't want. We don't want your system leakage, to your orthogonal space. But there's another use of this picture, which I learned is that how can you create high-order interaction term from like a, not high-order interaction, maybe like from 2-body to like a 4-body. The way is that you can try to put 0 here, and you really want this, the leakage part become high-order interaction. And this is some trick I learned experimental physics are using. So we use the same picture, but we use them in a different way. Okay. Just some technical remarks here. So let me show you some of the experiments we can do with this kind of idea. And this is on real machine. So this is really running on the real machine, and we use like IonQ. Not surprisingly, because I'm from Maryland, we have some budget in the computing time on IonQ. And so, for example, this is really, I say this is not really showing speed up, but really showing if you want to implement this particular quantum walk, how many so how much resource you need, right? So with our technique, we can do everything here using 14 qubits, one single qubit gate, like 102 qubit gates. If you're not using our encoding, this is the number of gates you need. So you see, this is not something just say unique for Hamiltonian model. You can also do that in a gate model, just to have a different way to map them. So it's really like a time-space trade-off. I try to use more qubits, but I get like a shallow circuits, something like that. And then you can do this not just for that work, you can also do this for spatial search on 2D, and this is something we run on IonQ as well. Yeah, that's the budget from Bracket. I don't know that is that true anymore, right? So, and you can still see there's like a constant factor improvement in the resource count, but this is really make the difference between you can run the experiment today or you cannot run this experiment today. Okay, and we can also do something, this is exactly related to the QHD case where I really want to run the Schrodinger operator. Of course, I ran this for one dimension. That's basically how we run this on IonQ. And this is something, we observed from the IonQ machine. I think 2 years ago, the machine might be improved. So this is the purple is the ground truth. The blue is the what we observe. While simulating the Schrodinger operator. Okay, and you can do this for Q error, and I think there we also engineer system, try to put them in certain shape and with certain distance, and then try to emulate this with this prediction function. Again, so this is some specific encoding we use, which we call antifermionic encoding. Yeah. So I think that's what we have from the Hamiltonian embedding. Okay. Now we move to the last part. So right now, we talk about like the algorithm, which is theory, and we talk about how we do the implementation, but still theory. Now this part is really talking about how we engineer them, but not engineering the experiment. So we say how we can build this software toolchain. To really implement everything. And also maybe by doing that, we can also think about what's the the good abstraction, how to make a compiler work with this kind of thing. And of course, this is very computer science, I should say. Maybe for most of the physics community here, it's more like something good to know. You know what computer science really think about this, right? So how you want to build it. But of course, I think you're going to appreciate because software toolchain can help you be more efficient. Can automate some of the tedious things you want to do. Okay, so now just going back to my picture. So now I really want to put the programming back. So I spend most time just talking about the algorithm design. So where's programming? Programming is that I want to automate everything here. It's going from your application all the way to the path schedule to your devices without, maybe without you thinking about how this happens, you just talk about what Hamiltonian you want to run. And this is a framework we developed called SimuQ. And this is something we developed like 2 years ago. So one thing I want to warn here is that the software haven't been maintained for 2 years. So it probably cannot be directly running for now. There are lots of dependency issues because everything changed. But maybe the idea here is useful. And hopefully, I think maybe some idea here can inspire future generation of programs to help reduce like your task as a domain users for quantum. Okay, so what's our motivation? So we're basically motivated by one thing, which is I think important thing in computer science, that we really want to fit abstraction with the machine and with your application. So that's the right combination can really make you more efficient. And this has been just appear a lot repeatedly in the history of computer science. And the very famous one is that we start talking about is like a very early time we have Fortran. That built on the assumption your machine doing floating point arithmetic, and you try to make that easy for scientific computing for domain experts, right? So that's the idea for Fortran, and we also have Anderson's. There's a tool called Simula, and that's really for modeling some like a queuing system in a probabilistic system. That's the first type of like modeling algorithm, and I think it really inspired the design for the simulation for quantum because it's a language to describe what the system looks like. It does not describe what the machine want to do. So basically, you just in the classical domain, you just say what your queuing system will looks like, and your compiler will turn that into some computer program to simulate the entire queuing process. That's what is very similar to what we're going to show here. You just describe what Hamiltonian you want to run, and I try to find a way to run your Hamiltonian for you. And of course, later on we have a GPU, right? So GPU. They use CUDA, and they use, maybe today you use like a PyTorch, or maybe for machine learning. There are different like reason for doing that abstraction because your machine is specifically good for doing one thing, and then that just motivates our region. So at least we know quantum is really good at doing like Hamiltonian simulation, right? Can we just use the Hamiltonian simulation as the major abstraction as a program language? So at least for the users, we can make things more intuitive. You don't need to worry about how you map your Hamiltonian into the machine because the machine is going to change, right? So the code is going to change, but the particular Hamiltonian you want to run, that Hamiltonian won't change, right? So that really depends on your domain problem, not depend on your implementation. So we try to say at least this is a very good way to think when you try to think of running in Hamiltonian simulation-related tasks. So it could be useful for both near-term and long-term, especially the design principles, not necessarily the software tool. Okay, but we indeed have the software tool. So let me just tell you a little bit more about the tool. So we have a website for the language. We have a Git repo, and on the website we have a tutorial. Give like IEEE Quantum Week. I forget which year. So the idea is that you're going to specify your Hamiltonian you want to implement, and we can map this to say Git-based machine. We have the connection to IonQ. Again, this is over 2 years ago. Interface can change. I don't know. At that time, we can also compile directly to the OpenPOS with IBM machine. Unfortunately, OpenPOS is no longer supported on IBM, and you can definitely compile to QERA. at the time. I think the interface also changed, unfortunately. But this gives you the idea, right? So from the user, you just need to specify what Hamiltonian I want to run. You just get everything dedicated to the compiler to help you to do that. And it can also be the case that there are different kind of simulation algorithm. There's strategy for doing the simulation, but this is different from the simulation target itself. So the user only specified the target. The compiler can be built to incorporate all different kind of simulation strategy. And in particular, when we design a SimuQ, we really try to think about, can we do the compilation directly leverage like a non-gate-based machine? So I think that's our unique strength. But at the same time, if you have the information of this target Hamiltonian, you can also do compilation with all this like gate-based simulation. You can try to incorporate that into the compiler, which is something we didn't do. But in principle, we can do that. We only have like a simple totalization here. So in the tutorial, we give it the trivial quantum week. We basically show with this kind of language and sending to trivial ion, we can reproduce the paper simulated 1+1, I think, Schrödinger model, but just with a few lines of code, we can generate all the figures from that paper. So maybe that's a good sign. You can make your life easier. But of course, there are caveats. Yeah. So now let me just try to tell a little bit of the idea, because most of you are not a computer scientists. So as I said, I try to see whether there's a way for this compiler to really make non-gate based parameters useful. Just recall, I can talk about he has all different kind of Hamiltonian they can engineer, but how can I make that kind of engineer into engineer feasibility into something compiler understands? So compiler can use those, can engineer the Hamiltonian to put together for some target Hamiltonian I want. So in order for that to do that, I need a way at least to describe what the machine's capability. And if you're talking about a gate model, your machine's capability is very easy to imagine. Just say, oh, I can do this kind of gates. Super easy, standard, and you don't have any trouble for that. Now, if you imagine you're dealing with all kinds of Hamiltonians from your system. So is there any unified way I can describe your machine's capability? So this is actually a conceptual motivation for this SimuQ project, and also we have a proposal. So we call this abstract analog instruction set. But what's its essential idea is that we observe. Maybe this is really very programmatic perspective from how you're doing your experiments. So no matter what platform you have, right? So you need to whatever operations or Hamiltonian operations you can do, they're coming from the control signals. So that means you really need to specify control signal, and that control signals when get to your system will trigger a Hamiltonian, and that Hamiltonian is parameterized by the signal itself, right? So this is the correspondence, and we just say, can we have a symbolic way, basically, a way the compiler can understand to describe your this kind of a control and Hamiltonian correspondence. So instead of saying, okay, my system or performing some gate, I would say when I send pulse in this way, my system will go over this particular say Hamiltonian evolution, and for how long will depend on how long my pulse is. So you really parameterize what you can do in terms of the Hamiltonian, or of course with the parameters to specify your signal. And you can write them down symbolically. Because right now, at least the most machines are controlled with control signals. Then you can just list all the possible controls you can do today from all the control lines you have. And then you have a way to specify all kinds of quantum simulators, especially for non-gate-based simulators. So that's the the idea. That's a rough idea how we build a abstraction for a non-gate-based quantum simulators, so the compiler understands. Okay. Now just a little bit into the inner working of the SimuQ. So from the users, the sense will be simple. you just write down your Hamiltonian you want to do. And the specific level or model here is that we imagine the Hamiltonian the user is going to write will be many-body Hamiltonians. Each side can be a spin or can be fermionic or bosonic modes. That's all it can be. Of course, you're going to have, say, quantum chemistry problem or maybe high-energy physics problem that's not direct like that. You need to have a translator to map that into the machine. But why we choose the many-body system is because this is roughly what our current machine is. Right? Our current machine basically have like a, no matter what technique you're having, it's still like a many-body system. You're going to engineer the interaction. So this is really like what the machine currently have. Of course, they might not have the exam, control or like connectivity, but it's the same type of Hamiltonian. So when we have that, we really simplify the task for the compiler, because it's very similar to the type of the Hamiltonian the machine has. For example, sorry, this is not the user side. This is the other side. So the other side is that the compiler will also take into a machine description. The machine description going to be another specific language, the SSL. You can list all kind of like the primitive Hamiltonian evolution the machine can do. But now, of course, written them in a symbolic way. Okay, so you provide a script. This is implementing Python. A script like this, talking about your machine's instructions, and this is talking about how you write your Hamiltonian. Of course, this is a language embedded in Python. You can use any Python syntax. So you basically, anything you like Python is still true. And what it generated will be this kind of pause schedule. I showed this picture for IBM Open Pause, but it's no longer available, unfortunately. But you can feel right. So the compiler really say, I have this kind of target Hamiltonian. I have capability from the machine running like this. Can I somehow schedule all different like the basic Hamiltonian programmability in a way so my effective Hamiltonian will be my target Hamiltonian. And we turn this into something compiler can do. So that's the essential things happening with the SimuQ language and the compiler. So let me just zoom a little bit, because I think we're probably not a computer science oriented audience here. So for example, if you think about like a readable atoms system, so this is like a at least like a QL used in the very first version of that is really treated as like analog simulator. So you can have like a laser to address each of the atoms. You can move the atoms around, and you can have some like different like detuning or whatever Hamiltonian can generate. So basically, you have a few different kind of Hamiltonian you can generate with your laser control, and something can be programmed. So this is basically how we encode those programmability into Python. So basically, we say for example for this one, I say there are some variables I just claim this is an additional variable that can be parameterized as input. The particular Hamiltonian will depend on the parameters here for these instructions. And when I given those parameters, I can generate this particular Hamiltonian to my system. And everything here is stored symbolically into the Python object. So those information will make compiler capable for doing this compilation. And of course, in the QR specific case, they don't have individual addressing. Probably I don't know if they still have. They used to be global addressing, so you cannot individually address them. So then you have a different way to write down those instructions. And you can also think maybe this is for IBM machine. I just jumped a little bit. So of course they're like slightly different from the machine's basic Hamiltonian and also the effective Hamiltonian after rotating wave approximation. But we deal with some cleaner version. In this case, you're talking about like your superconducting transmon can really give you some like one local interaction which parameterized by A. Give this like a local poly rotation or like a two. Body polyrotation parameters by some parameters that will determine the shape of the pulse. So you can have all those information into those files, and then so how we design a compiler for that. So very roughly speaking, So because you have all the information from your target system and your machine's capability, we can try to turn the scheduling problem into a big, like a satisfaction, constraint problem. So it's not a very efficient, I should say, but roughly speaking, that's something you can do. And then for that one, we can use something like a solver, try to solve for that one. There are more efficient way for doing that. They actually follow up a paper, say how we can make that solver more efficient, so larger system. For the very initial one, that will be sufficient for us to do. And when you be able to say, having us, it's really like you have a big, jigsaw puzzle, right? So you want to symbolically choose where you want to put the piece. For the system of current size, you can do that with the solver. And when you have some solutions coming off the solver, so basically like at what time you want to use what kind of instructions, then you want to schedule them, you want to, there are some conflicts you want to avoid, and also you want to transpile that into the actual pause on your system. So that's basically a few steps the compiler does. I probably want to just jump a little bit. I don't know how much interest is here, so this is really like a compiler building the design automation thing. It's more like computer science thing. This is just showing how we build this kind of solver, and we use the SMT solver to solve this problem. And we also avoid some like conflicts where you basically say there are certain instructions they cannot run at the same time. You want to avoid that, and you want to schedule this app, using process. So what this gives you, for example, if you're just users, we did a benchmark for this kind of elaborate Hamiltonian simulation. I think this is coming from a paper from Berkeley. They give you our benchmark on different kind of Hamiltonian simulation tasks. And we say, you can just encode them, and I can try to help you map this in this way, to different machine, and the compiler can work. It can work reasonably well at the time, even when your system is not huge. Of course, the huge difference to change over time. I think I should say there's like a recent paper improved this significantly by not solving everything as one single instance. You derive a heuristic, try to solve them using some divide and conquer method. Then you can deal with a much larger system for this kind of compilation. But from the user perspective, you don't need to worry about that. You just need to write down your Hamiltonian, you're done. Right. So and from the algorithm design perspective, so with this kind of program language, potentially you can think about how you can just design algorithm on Hamiltonian and try to implement them on Hamiltonian. So one thing we have done is that we have the QHD I just mentioned, and we do build the software we call the QHD op. So QHD op really makes use of SimuQ as an online compiler. So there's a target QHD Hamiltonian. We use Hamiltonian embedding to turn that into many-body Hamiltonian, and many-body Hamiltonian using SimuQ mapped to the real machine. We did that all the way to D-Wave and RNQ. Unfortunately, maybe you cannot run either of them for now. But that's something we show is feasible. It's possible to do this kind of tool. If you're really computer scientist, I think there are tons of things you can think about here, because this is really a computer science project. You can try to make the compiler more efficient. You can say also maybe from the domain applications, like maybe what we're going to see later in the school, you're going to see high-energy physics, chemistry. Can I make something more intuitive there, so I can directly map here? So I don't need to do again the implementation. I just need to write down the Hamiltonian I want. I like my compiler to really catch up with the implementation technology. Not you as the person to do that. And of course, I think another thing is, with all this program language for quantum simulation or quantum general stat, it's really tricky to get things correct. And especially for quantum simulation, you don't have ground truth. So maybe this is the kind of program language you really want to have really high assurance. So can we verify, your implementation of quantum simulation? I think that may be very important in practice. I don't know how to do that, and because it's really hard to get a ground truth. And also it's very tricky in the sense if you know formal methods is not really very compatible with complex numbers. We're going to see a lot of troubles here. Okay, and there's one thing I want to highlight here is that when we think about Hamiltonian as the first kind of object, there's actually something very natural. I didn't mention this is application, but I should. Is you can think about differentiable Hamiltonian simulation. So what do you mean by that? So we know there are a lot of, like I say, variational type of algorithm. You can do this for VQE, you can do this for QAOA, or you can do this even for control. But I want to say this is not something conceptually new in the sense that in the classical domain, we have also some for actually this is classical machine learning topics. We have like something called a neural ODE. We have something called differentiable physics. They're used to do, say, for computer vision or like for graphics or machine learning based like scientific computing. So those things are really showing powerful capability if you can really say make your dynamic system differentiable. And I try to learn those parameters all along the way, right? So I can somehow parameterize my dynamics and use the dynamic to do something. Sometimes you can get like a shorter implementation from the first principle implementation. Basically, you get a circuit model, but sometimes you can also use that to do optimization. But of course, very important thing for making that happen, which is also the from the program language or like engineering perspective that really happen in those classical machine learning models is that you try to make things auto-differentiable. So you really want to find a way you can make the continuous dynamic object in classical domain auto-differentiated. So it's actually true. We have a paper showing if you imagine Hamiltonian as the only thing, you parameter that, there's a way you can do auto-differentiation for quantum as well. So you can use parameterized dynamics, and there's a way you can run this as a quantum algorithm, and there's like some sampling algorithm, and they can compute a gradient for that particular parameters with everything running in quantum. And that particular thing can be easily implemented in SimiQ. You basically can have like auto differentiation of quantum dynamics, and this can be used. For example, we show some cases like you can use this to generate much shorter control, and you can of course use this for doing VQE. But we haven't got a chance to really run this on real hardware. So this is on simulators. And you see this appeared in New Rips like 2022, so a few years ago. We don't really have the hardware to do that. But especially for the control, what you really should imagine is that this is something you could have a machine in the loop and try to generate controls directly suitable for the machine. But you can rely on the entire like ML framework for doing that. I think people should try that because this is something a lot of people in classical domain like robotics or maybe like computer vision, people are doing that. People, especially you probably heard like the world model, right? So everything happening in the world model, there's something just following this kind of line where you do the training in this way. Okay, so of course, if you're doing hardware for SimiQ, maybe you mean that you can tell me what's the more capability of your machine can do, and if there's more trick, we can integrate it into the compiler. Again, so those are the things if you're in computer science and if you're interested in program language, I think it's something you can follow. But of course, if you're not, you just know this is something computer science people can do. And finally, I mentioned we have this QHD op, which is something we built on SimiQ. We did have a tutorial we actually gave on this year IEEE Quantum Week, and you can go either through this barcode or the GitHub. So what we're going to see is that I'm going to show you how you can run this entire thing. Of course, you can only run simulator if you don't have access to those commercial devices. But it also has a link to the QIHD. If you're interested in running QIHD, you can still using the QHD op. That can help you to maybe see some like a real practical result you can play with. And with that, I think I just conclude my lecture. Yeah, thanks.
Thank you.